Video section 3.3, day 2. We are continuing on with looking at increasing and decreasing functions, and we learned how to do the first derivative test on day 1. Now today so from there we were able to pick up increasing and decreasing functions. Today we're going to take it one step further and hopefully be able to identify where mins and maxes are occurring. So this, you can read it yourself too, but once you determine the intervals on which the function is increasing and decreasing, it's really relatively easy to find the relative extrema. There's the first derivative test that talks about the critical values and finding them, but in it we get a description here that if our first derivative changes from negative to positive, then we can conclude that we have a relative minimum occurring at that value of c, f of c. If the first derivative changes from positive to negative, so I was going up then down, obviously I'm reaching a peak here, and we would say we have a relative maximum. If I notice that the first derivative has positive values on both sides of some critical number c, or perhaps they were both negatives on each side of x equals c, then I have neither relative mins or max going on. So visualizing the first derivative test, and I'm going to show you justification with this. Here we have a curve, and on the right side I have positive slopes, and on the left side we have these negative slopes. Well, then I'm going up and down. F of x has a local max at x equals c because the first derivative changes from positive slopes to negative slopes at x equals c. The picture really does show it, doesn't it? In here, I'm looking at my tangent line, negative slopes all along here. Tangent lines over on the right here would be all positive slopes. And we can obviously see that this is a min value here. So f of x has a local min at x equals c because f prime of x changes from negative slopes. Oops, I need the word changes in there. Changes from negative slopes to positive slopes, from negative to positive slopes at x equals c. Down below, we kind of catch those special cases. Here I have negative slopes on this tangent line as shown. Here we'd have also negative slopes on the tangent line. So I have negative slopes all the way along this curve as I'm going down. I do have a critical value here. I can see how this curve just slightly flattens out here. So I do pick up, this is a critical value here where f prime of c was equal to 0. However, because I have neither a local min or a max, and that is because f prime of x is negative immediately on either side of c. So when I look to the left of my c value, my x equals c, I see negative slopes. On the right side, I have negative slopes. So I have neither a local max or a local min. Here we notice we have positive slopes all along this curve, continuing with positive slopes up through here. Critical value f prime of c would equal 0 at this spot. We flatten out, don't we? But it's neither a max or a min because f prime of x is positive immediately on either side of my critical value, x equals c. So let's do a little practice here. I've got example 3 for us to run through. It looks like it is a function that is a rational function. And rational functions we know are continuous functions that are differentiable everywhere on their domain. And usually that's, the key point is on their domain. So when I just examine the domain, which is a good thing to get in the habit of doing, the domain of this function has all x's just as long as x doesn't hit -1. and we're fine. So when it's -1, we notice our denominator goes to 0, and of course the function isn't defined there. We would expect a vertical asymptote on that. So let's find the open intervals in which it's increasing and decreasing. This is very similar to what we did yesterday. We are going to work with f prime of x, and that means we need to get our derivative. So we're going to have a 2x minus 2 multiplied by x plus 1 on the bottom. I need parentheses around my lead there, minus derivative of the bottom times the top, so a negative times x squared minus 2x plus a 1 all over the bottom squared, x plus 1 quantity squared. It was just some simplifying work. If we FOIL out the top, we're going to have 2x squared plus a 2x minus a 2x minus a 2. Send the negative through, we're going to have negative x squared plus a 2x minus 1 over that quantity squared on the bottom. Simplifying, we notice we got a positive negative going on there. I'm going to come up to the next spot here, and I'm going to have a 2x squared minus an x squared. That's an x squared plus a 2x minus 3 over our bottom squared. If I want to find increasing, decreasing, it is essential that I get my critical values. And those critical values are going to come from setting the first derivative equal to 0 or the first derivative not existing. So where does the derivative not exist? Well, we've been through this a few times, haven't we? I think it'd be beneficial to have that factored up on top. So let's take this one more step. X plus 3 and an x minus 1 over the bottom squared. Make that look more like a 1. Okay, factored form, fully factored form, those are nice to work with. I can tell where my derivative is equal to 0 simply by setting the numerator equal to 0. That gives me critical values of x equals -3 and a 1. Over where it does not exist, that is primarily concerned with the denominator. So where does my denominator go to 0? Well, that's happening at x equals -1. We can call it a critical value. However, keep in mind that it's not going to be a relative max or relative min because -1 is not in our domain. So we need to determine whether we have local mins and local maxes, but first I need to talk about that increasing and decreasing function. So I need a little space here to create the sign chart. So let's lay out our number line. We have a -3 as our lowest value. Next is -1, and then we go to +1, and I'm going to move my -3 up to the top. Those were my critical values. I'm looking at the sign of the first derivative, so I'll indicate that. Now, we need some test values. Well, something to the left, something in between, and that'll work. Those are my test values. Now, evaluating those, I need to take it into the first derivative. So f of -4, the fully factored form. So I'm spying this version right here. When I put in -4, I would have a negative times a negative divided by a positive. The bottom's always positive on that, isn't it? And that gives me a positive result in this region. I'm going to just go ahead and tuck these next ones in here. I've already pre-calculated it. And it looks like that for a sign chart. I can tell that I'm increasing, decreasing, continuing to decrease, probably flattens out at that -1. Oh, hold it. We talked about the fact that it is a vertical asymptote, didn't we? And then we're back to increasing function. So just be aware, you know, this is kind of a funky critical value here. It really doesn't exist, does it? We don't have -1 in the domain. So I can tell where my function is increasing. F of x is increasing on the interval from -infinity to -3, that critical value. Join that with the other region from 1 to infinity. just picking up our critical values of -3 and 1, and that concludes for the increase. Where is it decreasing? It is decreasing in that middle region, but because -1 is not in the domain, we need to use open intervals on -1. So I'll also have to write this as a two-part interval and join it with a union symbol. Okay, from this, that sign chart really tells the story to us, doesn't it? We're climbing up and then all of a sudden we're coming back down. We hit a max right here, don't we? I would call it a local max, maybe an L max. Here we are continuing down, continuing down. There is neither a max or a min going on here. Now, on this next one, I'm going down, back up. I hit a local min right there. So I'm going to write L min. Determine the x values for any local mins. So they said the x values, so that's what I'm going to reply with. At x equals, the local max occurs at -3. At x equals -3, f of x has a local max because we're going to justify this. What is our reason? Well, the change of the derivative. And when we did that visual description here, notice how we phrase this. F of x has a local max at a certain value because the first derivative changes from positive to negative. So that's how we're going to document our justification here. Because f prime of x changes, key word, from a positive to a negative, from positive to negative. Likewise, I can state that at x equals 1, there's our critical value, f of x has a local min because f prime of x changes from negative, notice on the left we had that negative to positive on the right side of our critical value. And that's all it's doing. Really not bad. Those sign charts are so useful. Okay, so example 4. Why don't you try and do the derivative? You know, one thing I might suggest is anytime I see those radicals and I need to take the derivative, I'm going to immediately switch it up into a fractional exponent or rational exponent if you'd prefer to call it that, and then work from there. So I'm going to hit pause. I'm going to do up the work and get my derivative. You do likewise. Okay, I've got the first part sketched out. It's just the product rule. I'm sitting with this now. I know if I'm going to end up finding increasing, decreasing, I need my critical values. I need to be able to set this equal to 0. I have a fraction plus, you know, a little polynomial there, or just a term. I need to be able to pull this together. So, like denominators, and you know, one easy way is to cross multiply and get those values. So I'm going to have a 4x minus 2 plus, now I'm going to multiply crisscross here, 6x to the 1/3 times x to the 2/3. It indicates I should add my powers. That comes to a full power of 1. On the bottom, then, my common denominator would be the product of those two denominators. And there's my result. Now, I can certainly simplify this just a titch more. Sorry, that's kind of moving in on this, but I want more space. All right, so we're going to have 10x minus 2 over. Now, if you wish to see it as the radical that it truly is, you can write that. And here's my h prime of x. In order to find my critical values, let's go after those, the critical values. The critical values are happening when h prime of x equals 0 or when h prime of x doesn't exist. The place where it equals 0 is take your numerator, right? That would say that x is 1/5. Take your denominator for the does not exist. So when is the denominator equal to 0? That's equal to 3. Cube root of x. Divide by 3, we get 0 is equal to cube root of x. Cube both sides and x becomes 0. I have two critical values. Critical values are x equals 1/5 and a 0. Take it to, oh, I'm going to be tight here. Take it to a sign chart. Go ahead and sign chart it and see if we match. Okay, so I got my sign chart drawn out. We had those two critical values at 0 and 1/5. So I found some, quick little easy test points, and I used -1, 0 to 1/5. So I just halved this fraction, and that gave me 1/10. Easy way to find a number smaller than it, double the bottom. And then I chose 1 to the right side. I tested each of these out, and you can see kind of my analysis done there, and I got positive, negative, positive. So we have an increasing function, a decreasing function, and an increasing function. This will hit a local max. Here we hit a local min on that critical value. So could we talk about areas of increasing and decreasing? Absolutely. I know where my local mins and maxes are. So to write this up, I might just sneak this in. Find the open intervals in which we're increasing. So h of x is increasing on the open intervals -∞ to 0. Union that with 1/5 to infinity. H of x is decreasing where the first derivative is negative, and that occurs on the interval between 0 and 1/5. And I certainly could justify those, and I kind of spoke it as I said it is decreasing. And I could put in here if I had to, because f prime of x is negative on this interval. That would be a quick way to justify it. Now, where do we have local mins and local maxes? Determine the x values. It's nice to keep going with x values. So at x equals 0, h of x has a local max. How come? Because f prime of x changes. These are the ones that you have to talk about the changes from positive to negative. We go up and come down. At x equals 1/5, h of x has a local min because f prime of x changes from, now we just got the reverse scenario, we're going negative down to positive. Cool. All right. A little bit of different stuff coming up here. Particle motion, motion along a line. Let's think horizontal line on this one. So we're given a function s of t, the position function, that describes the motion of the particle moving along a line. For each of these functions, oh, we only got one function here. For the function, find the velocity, identify the time intervals when it's moving in a positive direction, identify when it's moving in a negative direction, identify when it changes direction. The cool thing with this is, well, we've already studied a little bit about velocity. I know to get to velocity, v of t, that is equivalent to taking the first derivative of the position function. So my velocity function will equal 2t minus 7. That's a first derivative. It too has critical values. We can take that first derivative, set it equal to 0, and get critical values, just like we did on those other functions. So critical values, take my first derivative, s prime of t, which really is like taking the velocity function, setting it equal to 0. When is the particle stopped? When doesn't it have any velocity, right? So I have 0 equals 2t minus 7. I get a critical value of t equals, add the 7, divide by the 2, and I got 7/2. So what's neat about this is we can use that first derivative sign chart to help us decide when the particle is moving in a positive direction and a negative direction. Put it on our sign chart here. This is our t-value, and it is at 7/2. I can pick up the velocity, or you can write, it's also s prime, isn't it? Plugging in something to the left. Well, this is like 3.5, so let's plug in. We're locked in at 0 here. Remember, our time started at 0. So let's throw in 1. Something bigger than 3.5, let's plug in 4. So something a little, or right at 1. When I plug in 1, I have 2 times 1 minus 7. 2 minus 7 will be -5, so it's a negative. Plugging in 4, I get 8. 8 minus 7 is 1. That's a positive. This tells me that I have a positive direction, and on linear movement, positive direction is interpreted as our particle is moving to the right. And on this one, I'm going to just draw a squiggle in here. This is negative direction, which can be interpreted that our particle is moving to the left. What's happening right at 7/2? At t equals 7/2, our particle is standing still. Particle is standing still for a temporary moment, right? And that's the point, and is the place where it changes direction, where the particle, rather than using the word it, the particle changes direction. So, particle movement, very, very similar to working with, graphing functions, still interpreting that first derivative sign chart. Kind of nice. Reading a derivative graph. So, this is kind of unique because look what they're giving you. They have given you a derivative graph. Normally we have the original function. So what kind of information do I have when I have a derivative graph? Well, I want to get some tools here. What I know about a coordinate plane is above the x-axis I have positive y values, right? Positive y values reside above, negative y values reside below. So anytime this graph is sitting above, it's telling me my derivative, f prime, is greater than 0. And when it's residing below, down here, my first derivative is less than 0. So I have increasing and decreasing functions off of this. I can pick it up. So what is happening when it resides on the x-axis? Well, that's where my f prime is equal to 0, right? Let's just do a quick derivative sign chart on this. My critical values are coming right off this x-axis. I notice that I have one at -1. I have it hitting at 0, and my function crosses also at 1. So those would be my x values, which are my critical points, and my first derivative. Now, it's sitting above the x-axis here, so that would be a positive slope. It's sitting below the x-axis when I'm between -1 to 0. When x is between -1 to 0, I have negative slopes. Then I am above the x-axis between -1 and 2. So I'm back to a positive slopes. And I'm sitting below the x-axis, so I have a decreasing function there. Estimate the values at which it has a relative max and min. Well, now I'm back to my same old game, and I can easily pick up that I have a local max right here, a local min right here, a local max right there. So, I'm saying right there, but I'm meaning local max at x equals -1, local max at x equals 0, local max at x equals 1, those critical points. That will take some practice. We will work on those. Reading derivative graphs. All right, this is getting long, but I'll see if I can sketch this through. All right, so I gave you an example of this first one. It has 3 graphs given. Can you figure out which is the original function, the first derivative, and the second derivative? This right here is my original function. It's a cubic function. If I take a derivative, it knocks me down to a third power going down to a second power, which would be quadratic. This right here is a quadratic function. It is my first derivative function. Notice how it is quadratic. If I took another derivative, I would be going from quadratic to linear. That describes this one. This is my f double prime, and it is a linear function. Sometimes just thinking about the powers or the degree of the functions can help you sort out which is your original function, your first derivative, and your second derivative. So 58 and 60, these are problems out of the book. And we can split this thing up. So this is an original function. Get used to just identifying what am I given. I'm given an original function. I want you to sketch the derivative of this. So I want you to come up with the derivative graph. Well, in my mind, I see that this is a quartic function, perhaps. So that would be of degree 4, wouldn't it? If I knock it down when I'm kind of expecting my first derivative to be cubic in nature. And I have a general shape in my mind on that. Now, slopes along this first region, would we agree that that is a negative slope all along that region? I'm going to sketch just a quick sign chart down here. So I have negative slopes in this X region. Here I hit a critical value. How do I know I hit a critical value? Because I hit a flat horizontal tangent line. So when X is, let's call it -1 here. When X is -1, I hit a critical value. That's a V there. And its slope would be 0 there. I also have another critical value at 0. And I have another critical value at 1. So this is kind of tight here, but we're going to fit them in. I know that because I see those horizontal tangent lines, right? So negative slopes all along here. So I indicated with the negative sign. Between -1 and 0, this region there, I have positive slopes. So I'm going to put a plus sign right here. In this region, let me grab a different color. In this region, I'm back to negative slopes. So here's a negative. And finally, back increasing function. For increasing functions, our derivative will be positive. So I want my derivative graph to be negative, then go to positive y values, negative y values, positive y values. So this is going to be negative y values, positive y values, and you get the picture, negative y values, and back to positive y values. It's going to tell me where my function should be landing as I plot it. So I have negative. I have a very, very steep negative slope here. That means I'm going to start down low where I have larger negative values. So I'm going to be coming up. I need to strike my graph at 0 here because the slope is 0 there. Then I go into positive till I come back to a 0 slope here. So there's a little time frame where I'm above the x-axis for positive y values. Then I'm going to go back below so that I have negative y values, coming back up at 1 here where my slope was 0. So I'm down below for a little bit, and now I'm back above, heading like that. Does that turn out looking cubic in nature? It did, didn't it? And there's the first derivative. Okay, that is great. Number 60 I didn't get to. See you later.